I didn't make sense.
Okay, let's get started. So we're in the midst of learning about how to analyze flow through aquifers by solving this groundwater head equation. And what we saw last time was kind of this procedure where we want to determine the hydraulic heads and the flows in a particular situation. And the way that we got here was to take a look at the hydrogeology of kind of a sketch of it, but still fairly realistic. And then based on this, we did some simplifications and we came up with a conceptual model that is this. And this then we can use to solve the problem. So what we're going to do is say that this is represented by a confined region, and in this case, the confined region means that the place where the flow is occurring has a uniform thickness. Okay, we still can have recharge coming in, like we show here, and the conditions at the two ends are based on these streams. And this one says that the head at this end of the problem is equal to the stage of the stream, or the hydraulic head at this in the stream, and same with this end. Okay, so then the question that we're interested in is, what does the hydraulic head look like here? What's the flow look like? And in particular, we are interested in finding out about the divide, because in some cases, we think the divide might be in the middle, but here, at least the way this is drawn, it looks like it's off center. So we might want to, well, what we're going to take a look at is what's controlling the position of the divide. Okay, so there's the conceptual model. And we went through the, we need to go through these characteristics to determine the form of the equation. So it's a 1D problem. It's steady state. There are no changes of the hydraulic head in time. It's the aquifer is homogeneous, isotropic. There's recharge, and we're assuming here that it's confined. Okay, so those are the characteristics, and based on that, we have a governing equation that is this, and this was the same governing equation as we had last time. For these fairly simplified conditions. Okay, so this is the overall approach, and we've gotten through the first two steps. So we've got a conceptual model based on the hydrogeology of the problem, and we've got the governing equation, and the boundary conditions are remember we write them as equations. It's a very simple equation. It just says that the head is equal to h1 at this location. So that's x equals 0, and the head is equal to h2 here. Okay, so we now have enough to solve the problem. And the strategy is going to be the same as last time, where we have a governing equation, which we said was this. We're going to integrate it once, twice. You get the hydraulic head with constants, and then we're going to use the constants to solve for the boundary conditions. So we integrate once. We got a second derivative here. We integrate once, we get a first derivative, and we integrate this side. Yeah, this is constant, so we integrate a constant, you get a function of x, and there's another constant of integration. we integrate again. Okay, so if you look back through your notes, we did this last time, we came up with the same result. Okay, well, it was the same Governing equation. And so we get this same result. We're going to solve the constants using different boundary conditions, and that'll cause the ultimate result to be the same. But at this stage, it's the same as we had last time. So the boundary conditions are that H equals H1 at x0 and H equals H2 at xl. Okay, so let's use the one where we have x equals 0, right now. Because we can just say H equals H1, this equals 0, that equals 0, and then we're left with C2. So that makes it easy. This one, we're going to set H equal H2 and substitute in L and X. So that'll give us H2 here, and then we have minus R AB, that would be L squared. And we already know that C2 is equal to H1, so I'll put that there. Okay, so that's all the info we have substituted in here. That's what we're interested in. So I'm going to subtract H1 from both sides. And if I do that, I get H2 minus H1. And then I'm going to divide all the terms by L. So if I divide this one by L, L here, that's going to get rid of that squared. And then I have L over here. Okay, and that L. So now I need to add this term to both sides, and I'll have C1. So I'd like C1 to this stuff here plus that. Okay. So one thing we can do is just check the units. So the units of H and L are the same, so these cancel out. So just this is dimensionless. R and K, those units are the same. L and B, those are the same. So those cancel. So we're good there. Okay. So now this goes back in there. And this one goes in there, and we'll have result. Let me see if I can just do it like this. So minus come up here a little bit. So that's H. So we can check this. One thing that it needs to do is satisfy the boundary conditions. Okay, so if x equals 0, then H needs to equal H1. So if x equals 0, that's 0. That's 0, that's 0. H equals H1. So we're good there. So if x equals L, then this is RL squared over 2KB. If that's L, then this is RL squared over 2KB. So this and this cancel. And if that's L, then that cancels with that L. We have H1 minus H1. So if we substitute in x equals L, everything cancels out except with that. So we're good. Boundary conditions are satisfied. So this is what the hydraulic heads look like. We saw last time that we had a negative parabola, and here's that second order term here. So this right here looks like this. This, though, this is a linear function. So this looks like that. And then this is a constant, lifts everything up. Okay, so what we get from just inspection of this is we've got a curvature like this, and then this term kind of tips. And this raises it up so we can hit that boundary condition. Okay, well, remember with this problem, what we have is that the heads on the two ends are different from each other. And that's this term here. So this is what's tipping it. So that's going to be a kind of a new form, and we see that gives us this asymmetry. All right, so that's going to end up. Well, I'll show you what it looked like when we plot it up. I think about that here. Yeah. Okay, so here's what the plot looks like. So I guess one thing let's take a look at this. So here's R over K, that ratio, and there it is. So our recharge and conductivity appear together. It's actually recharge and transmissivity, but these are the same units. So these, you can think of that just as a dimensionless ratio. So there's R and K appearing together. And what I did was to plot this up with this R over K ratio. So here's what it looks like. And I guess another thing that I'm doing here with the plot is I'm writing this as x over L. So this is a little trick, kind of makes it convenient. What you do is multiply and divide by L or L squared. So that makes that x over L squared, and then do the same thing here. That cancels. Okay, so I can write this as a function of xl over squared, x over L squared, and this is x over L. Okay, so now when I plot it, I have this, and that's convenient because this side now just goes from 0, or the x-axis just goes from 0 to 1, instead of 0 to, you know, 1,000 meters or some actual dimension. It just makes it easier to visualize. And then R over K, these values 0.001 to 0.005. These are values that are typical for the ratio of recharge to conductivity around here. So around here, the recharge is annually is about like this, 6 inches to a foot or so. And the typical hydraulic conductivities, you work through it and you get a ratio of this. So what that allows you to do then is to plot this up with these different values of R over K and ranged by a factor of 5. And that then gives you a scale here. This is H, 25 meters. And there's 10 meters and 20 meters or 25 meters max. So this is the hydraulic head above the level of the streams, and it ranges from 5 to 25 meters. So we have streams around here that are separated by about 1 kilometer, and the water table rises up between 5 and 25 meters in between the streams. So this would be, this would be high ground, and the water table is now in the subsurface and raised up by this much. Okay. When you have an uneven hydraulic head on these two sides, then it tips it. And we can see that for when these two are at the same heads, the divide is right here in the middle. But when this head is higher than this head, then the divide here is kind of close to the middle, but then it moves over here and over back here. So the divide is moving as this recharge to conductivity ratio gets to be smaller. So that's, I don't know, when I first saw that, it was a little unexpected. I thought the divide ought to be in the middle, but pretty clearly it's not. It's kind of moving towards the uphill side. Okay, so let's take a look at why that would be. So here they're plotted, well, here's it, it's plotted for some extreme cases where you can see for this case, the divide is right here. So it's moving very close to that stream. And then in this case, we don't have a divide at all. So if you had this kind of situation, this stream here would be losing water. See how the gradient is going like that. So if there's if you have this or this case, this stream is losing and it's flowing down here to that stream that's gaining. So we can get some insights by determining where the divide is. Okay. So let's see. We have this situation, this is the divide, and what I'm going to do is say that there's X, and this distance to the divide, I'm going to call it X of D. So the distance to the divide, we'll determine that by saying that at this point here, the slope of the hydraulic head is equal to 0. Okay, that'll be the characteristic of a divide. So as I divide. pH at 0. Well, this is what we said dH dx was. So we can say that that equals minus R d x of d, right? Because it's at a specific location that the gradient here is 0. And then we're going to add in C1, and this is C1. Okay, so this gives us then a way to solve for XD. So I'm going to bring this over on this side. Okay, this is a minus sign, so it comes over here, it becomes positive. And then I'm going to multiply both sides by AB over R. So if I do that, this side can cancel out. This side okay, so we do it on this side and these cancel. We're just left with that. Here's KB over R. Here's KB over R. But with this term, that cancels with that. That cancels with that. So here's what we're left with. Okay. So let's try to interpret that. So this is the distance to the divide. And we can see it's got two terms here. This has got the difference in the heads on the two sides. And then here's our R over K ratio. So they're still showing up as a ratio. One of the things we can see is if H2 is equal to H1, then XD is equal to L over 2. Okay, so if these two are equal, it was that first plot on the top, right? If the hydraulic heads are the same on the two sides, then the divide is just in the middle. So that seems right. And then if H2 is bigger than H1, then this will be positive, that'll be positive. So what this says is that if H2 is, well, what this side says is the divide is gonna move towards the side with the higher head, assuming that that's positive. Well, we have to have some recharge for this to occur. So this will always be positive. So this is saying that the divide is always going to move towards the side with the higher head. So we saw that in the plots. Gonna move in this direction. So that makes sense. We also said that, or we also saw from the plots that there might be a case where there is no divide. So what happens is, the way that plot was going is that as this gets bigger, the goes like this. And then at some point, the divide, at some point you have a case where the divide is well, for sure if it's just linear, then there's no divide, but you can actually have a case where there's a very slight curvature and there's no divide. So that will happen when this equals L over 2, right? So if the divide is moving this way, when it reaches here, then there's no divide. So if the divide moves all the way over to the far stream, then there's no divide in between the streams. So that happens when no divide. Okay, so this thing gets to be equal to or greater than L over 2, then there's no divide. What's causing this to become bigger is if this were to be the same just for or stay constant, then as the recharge gets smaller, then this whole thing gets bigger. So what happens is when you have lots of recharge, the divide is probably fairly close to the middle. And then as the recharge drops relative to K, the divide moves towards the stream. Okay, so with just this simple analysis, we can get some insights into how to think about hydraulic head distributions between streams and the divide, the position of the divide between the streams. One thing to keep in mind is that the recharge varies through the year, and it also varies on a longer time scale depending upon the rainfall. So if this is changing, that means the position of the divide is changing. And usually we're thinking of the divide of watersheds being a topographic feature, and it doesn't change. But actually the divide for groundwater can change as the recharge changes. That actually has important implications, because what often happens is, if this is the ground surface here, people like to build factories up on the high ground between the streams, right? So often will have a factory here, and that's where a lot of times they make mistakes in their material handling and their groundwater contaminants. And so if you have groundwater, if you have contaminants coming in, the position of the divide determines what direction the contaminants flow. So if the divide's moving back and forth, you can have them flowing this way part of the year, and that way another part of the year. And there are several cases right around here where that kind of thing happened, and it causes a lot of confusion, because you first of all go and start chasing a plume in this direction and understand that, and don't really realize that there's also this thing happening because of how the divides move. Okay, so very good. This KR ratio is an important control, and I think we've learned some things about how to estimate the location of a divide. So what I want to do now is expand up our capabilities to evaluate these same kinds of issues, the hydraulic head and the flow, in an unconfined aquifer. So when we did the conceptual model for this last case, we assumed that the flow, the region where flow is occurring was at a uniform thickness. And you know, as a first cut, that seems okay. But I mean, the drawing itself had the saturated thickness varying in facially. So, you know, it's a pretty basic assumption that we're making, and we would like to modify that. So turns out we can fairly easily within the same framework of what we've been doing. So what I want to show you is how to analyze the hydraulic heads in unconfined aquifer. We'll get the governing equation and solve it using this same approach that we've been. Okay, so here's a reminder. What we've been doing the last few classes is solving this groundwater head equation analytically. So we go and use some mathematical techniques and end up with an equation that says what the hydraulic head is. We'll look at two other ways of solving it. One is a graphical method, and then also with groundwater models. The graphical method we'll talk about next time. And it requires a little bit of a artistic touch. And it'll require a little bit of kind of trial and error sketching. So bring a pencil and a good eraser, because in order to get this to work right, these are flow nets that we'll be drawing. In order to get the flow net to work right, you're going to have to draw some trial lines and then erase them and try again. So you need to have an eraser. Okay, so let's go back to this conceptual model and say, well, we analyzed flow between two streams, and we did it with by kind of changing the conceptual model that we see here and saying that the flow saturated thickness was uniform. But let's see about relaxing that. Okay, so this is an unconfined aquifer, and the saturated thickness varies all through the problem. Okay, so when we did the analysis, when we went and came up with the governing equation for the confined case, we started off with a volume balance, and we did the volume balance, the flow in is the flow out, plus the change in volume stored. So we're going to do the same thing here. We'll start off assuming that Darcy's law is okay. So if we assume Darcy's law is okay, and we use the Darcy's law for the volumetric flow, then that's the flux times the cross-sectional area. And the flux, we said, was minus K H X. And the area, so here's the water table. Here's the base of the aquifer. And this is a cross-sectional area here that's perpendicular to the flow. Okay. So this blue square or rectangle has a height equal to h and a distance this direction of delta y. So this would be h delta y. Okay. So Okay, so that's just this Darcy's law. Now we have something that's a little peculiar here. This is the gradient, head gradient, but this is the head right here. So this is different than what we had before. With confined aquifer, we would have the aquifer thickness here. But now we have the hydraulic head itself. So this is variable, that's variable. So that's going to change things. And what I want to do is call, if we take the derivative of h squared, then that's this. Remember from calculus? So if I divide by 1/2, then h dx is equal to 1/2. This is the derivative of h squared. Okay, that's the derivative of h. If we squared h and took the derivative, that's what that means. That's what that means. Okay, so this thing right here, we can write it like that. So Q is equal to minus A over 2 times the h squared. Okay, a little bit of a twist on Darcy's law for the unconfined case. Yeah.
Don't you need the delta y still?
Oh yeah, yeah. Thanks. No, we'll get rid of it here in a second, but it needs to stay here. You're right. Okay, so now let's go and do the volume balance. So there's the Darcy law version that we had right here, up in the upper right for as a reminder. Okay, so here's our control volume. So we'll have flow coming in, flow coming out. And right here, it's a little hard to see where the screen is set up, but we've got recharge coming in. So the volume balance is just Q in, Q1 is Q coming in, and then we have recharge coming in, and this is delta X, and we've got think about, this is really like a prism, that's delta Y right there. Okay, so R is the recharge flux, and it has to be multiplied by delta X. So the Y has, this is a volumetric rate, that's a volumetric rate now. Okay, and that's going to equal the flow out. And if we were going to be complete, we'd have the change in volume stored, but we're just going to assume that it's steady state for now. Okay. So what I want to do now is to recall when we did this last time that we related the flow out to the flow in and the rate at which the flow changes. So we have this. And we said this was like the first term in Taylor series. That's the gradient, that's delta X. And you can think of it conceptually that this part of the gradient and that delta X kind of cancel. So it's Q2 is equal to Q1 plus a little change in Q that occurs over that length. So this goes in there. These two cancel and the delta X cancels there. And I'll bring this over on the left side. So this follows pretty much what we did with for the confined case. We started off with volume balance, then we went to Darcy's law and put Darcy's law in here. So take this and substitute it in, and I'll just write it in kind of a simple way. So this take that ddx operator, and I'm going to substitute in all of that stuff over there. Okay, it's just substituting that in there. Okay, well, the minus sign will come out. Delta y, this will always be a constant, so it comes out. And if it comes out, then there's a delta y over here. So the delta y is the result. And let's say that it's homogeneous. That's what we had last time. So if it's homogeneous, this is saying take the derivative of that times that. And if these are both variable, you have to take the derivative of that times that plus the derivative of that times, well, the derivative of that times that plus the derivative of that times that. But if this is constant, it just is going to come out, and we just are going to have this operating on that. Okay, so let's write this as it's homogeneous. Okay, and then one more step. So I'm going to take this stuff, bring it over here, and then this says the derivative, take the derivative of that. That's the second derivative. So we get the second derivative of h squared is equal to minus 2r. Okay. Okay, so there's the governing equation for the hydraulic heads in an unconfined aquifer. It's one dimension, steady state, there's recharge, and it's homogeneous. So the same conditions that we had for the problem that we just solved, but now it's unconfined. Okay, so if you think back to the previous equation, it looks pretty similar to this, but there's some important differences. When we did the other one, we had the second derivative of h. This is now second derivative of h squared. And we had r over kb. There's no b in this problem. B was the saturated thickness of the confined aquifer, so it doesn't appear here. And then that too has popped up. Okay, so some similarities, but also some differences. So there it is. There are all the cases. And then here are the, here I wanted to do a compare and contrast. So that's what we had last time. So still have a second, it's a second derivative proportional to r over k. Here, second derivative proportional to r over k. This one is second derivative of h, that one's second derivative of h squared. So there are some differences. The strategy that we'll use to solve this is that it turns out we can use similar approach for solving that basic equation, and then we'll need boundary conditions. So the boundary conditions that we have for this case are going to be essentially the same as the boundary conditions that we had for the first case. So we have a type 1 condition where we would specify the hydraulic head, and a type 2 where we would specify the flux or the hydraulic head gradient. And then we need at least 2 of them for a 1D problem, for 2D and 3D. Okay, so here's another compare and contrast. The conceptual model that we had last time, and then this conceptual model where saturated thickness is changing spatially. Okay, so we've got boundary conditions. Now we need to solve for the hydraulic head. Okay, well, let's take a look. There's our governing equation. All right, so we want to solve this. What do we do? What did we do last time at this point? Disagree? Sure, integrate both sides. So if we integrate this, the second derivative, we integrate this, what do we get? Integration is like the antiderivative, right? First derivative of h squared. So ddx of h squared. And integrate that, we get, this is just a constant. So we integrate a constant, we get that, we get the linear function, and then a constant integration. Procedure is the same as last time, where next step is integration. We go from the first derivative, it just kicks out now h. This is minus r. Those twos will cancel. So solving it is pretty easy in this case. And now we have to apply the boundary conditions. So have enough we have enough time to do the first one. That's the easy one. H equals H1 at x equals 0. So that's 0, looks like H. Like H1 squared is equal to D2. And the other one is the H2 at x equals L. So H2 squared. Okay. Okay, so there it is, and there's C1. And I think solving for C1 would be a good thing for you folks to do in your spare time. So maybe we can start off there next time. If you have C1, then that'll be great. And we'll show you how to wrap this out.